Hi students, we are going to talk about the set of real numbers, and we're going to talk about them from the perspective of what we call the closure property. So there are some other links on this content page, and you definitely want to also look at those links regarding the real numbers, because in this quick screencast, I'm going to talk about the real numbers from the perspective of the closure property. And I'm not going to write the definitions down here necessarily, because they are going to be written on those other links that you can look at. So the first thing we need to know is, what does the closure property mean? All right, it's just best to start with an example. So let's say we start with a set of numbers. And the set we're going to use for right now is the set of odd numbers. And you can see them listed inside these brackets, and you've got the ... that says it keeps going following this same pattern. So here's how closure property works. I pick either one or two numbers from this set. I perform an operation on them, and when I do that, I get an answer. I take a look at the answer, and I ask myself, hey, is that answer one of the numbers in that set? If it is, then we say that the set is closed. If I pick a number or a couple of numbers and I perform an operation on them and I look at the answer and I say, hey, the answer is not a number that's in this set, then I say it's not closed. All right, so here's some more specific examples. Again, we're going to work with the set of odd numbers. You can start with any set of numbers. So you're going to see problems later where maybe you start with even numbers or just negative numbers or what have you. But this is what we're using right now, the set of odd numbers. So what we're asking is the set of odd numbers closed under multiplication? So what I need to do is just kind of think to myself, hey, if I pick any two numbers from this set and I multiply them and I look at the answer, what do I see? So I look at 7 times 9 and hey, that's 63. That is an odd number. It's part of the ... part, but it's there. How about 9 times 3? That's 27. That's an odd number. How about 7 times 11? 77. That's an odd number. So we're starting to see a pattern here. We are getting odd numbers back over and over again. And if you think about it, if you're adding, because multiplication is repeated addition, if we're taking an odd number and adding it to itself an odd number of times, that answer is going to be odd. So when we answer this question, is the set of odd numbers closed under multiplication? The answer is yes. Whoops. It is closed. All right. So our next example is a set of odd numbers closed under squaring. So squaring means raising it to the second power, which means multiply by itself. Okay, so I get 49. 11 squared, 121. 3 squared, 9. All right, so we're seeing the same thing happening here. We keep getting back odd numbers that are part of this. So again, our answer is yes. It is closed. All right, is the set of odd numbers closed under addition? Let's pick two. How about 3 plus 11? I get 14. That's enough to tell me, no, it's not closed. I only need one example. It's a counterexample. So it tells me that no, if I pick two odd numbers and I add them, I do not get an odd number back. I happen to get an even number back. So here I say no, not closed. All right, finally, is a set of odd numbers closed under taking the square root? Well, square root of 9 is 3. Yeah, that works. The square root of 11, though. If you pick up your calculator and you do the square root of 11, you're going to see that comes out to kind of a weird number, 3.31, and then it just keeps going and going. So we're going to have to say, hey, that is definitely not an odd number. So no. The set of odd numbers is not closed under taking the square root. All right, so we're going to use this idea of closure to develop the real number system. So all of the different sets of numbers that we work with in mathematics. So we're going to start with the simplest of numbers, and those numbers are the natural numbers, which we've already talked about when we were doing proofs. Sometimes they're also called the counting numbers. The natural numbers are 1, 2, 3, 4, 5, and so on. And you see I've written them in this little box. And so I'm kind of thinking of this in terms of closure. So we're going to start talking about operations, and we're going to see whether or not the natural numbers remain closed. So let's say addition. So if I pick two numbers and I add them, will I get a natural number back again? So pause for a second, think about that, run through some examples. If you do, you're going to realize every time I pick two natural numbers and add them, I'm going to get a natural number back again. To try multiplication. Do the same with multiplication. Think about it. If I take two natural numbers and I multiply them, will I always get a natural number back again? Again, the answer is yes. Next step would be to do subtraction. And think about what happens with subtraction. Two things happen. I could do something like 3 minus 3, and when I do, I get the number 0. And if I get the number 0, that is not a natural number, and therefore the natural numbers are not closed under subtraction. And so I end up needing another set of numbers. So inside here, we have our natural numbers. 1, 2, 3, 4, and so on. And then right outside of that, we have the whole numbers. And the whole numbers are almost the natural numbers, except they include 0. So it takes care of the situation where we take two natural numbers and we subtract the natural number from itself, and it gives us 0. But we also know that another situation can happen. And that is, I'm going to have to go back here and put these in. So the other situation that can happen with subtraction is if we take a larger number and we try to take that away from a smaller number. And I don't know about you, but I remember pretty distinctly in elementary school, even though that was eons ago, that my teacher told me you can't subtract if the first number is less than the second number. That really wasn't a smart thing for a teacher to say. Instead of saying you can't subtract, the answer should have been we don't know the right kind of number to use as the answer. Because you certainly can subtract, and you end up with what we call the integers. So the integers are the whole numbers and their opposites. So we've got the 0, 1, 2, 3 that keeps getting bigger. And then we also go the other direction, the opposites of the whole numbers, which are the negative numbers. And so that's our integers. So integers get us pretty far. If you take any two integers and you add them, we want to know, are the integers closed under addition? So pause, think about that, and the answer is yes, they are closed under addition. You can do multiplication. You take any two integers and you multiply them. You're going to get another integer back. If you take any two integers and you subtract them, you're going to get another integer back. However, this is not, those three operations, addition, subtraction, multiplication, are not our only three. We also have division. So if you take any two integers and you divide them, do you get an integer back? Sometimes yes. And if you do 8 divided by 2, you get 4. But sometimes no. If you do 3 and you divide it by 2, you get 1.5. 1.5 is not an integer. So we're going to need yet another set of numbers. So this new set of numbers that we get when we divide two integers are called the rational numbers. And that's the definition of rational numbers that I like. So I'm going to write that down. Let's say the result of dividing, I can't spell dividing, sorry, two integers. Right? And various things can happen when you divide two integers, and often we write division with a fraction bar. So I could do, say, -4 divided by 2, and that's -2. And I get an integer back, but it's also a rational number because all integers are rational numbers. I could do something like 3 divided by 4. And 3 divided by 4, I can leave it as its fraction, or I could change it to its decimal form, which is what we call a terminating decimal. And then one other thing can happen. We could do something like 2 divided by 3, and 2 divided by 3 is 0.66666. It goes on and on forever, and it's what we refer to as a repeating decimal, and the only way to write it is to use a symbol, which is a bar over the 6, to let people know that the 6 goes on forever and ever. Because it's not accurate for me to say 2/3 is equal to 0.6666666. I can't say that because this is an approximation, but it's not exactly the same. This is not quite as big as if I added just one more 6. Or one more 6, and so on. So those are not equal. They're close, but they're not equal. This is the only way I can write it if I want to say that they're exactly equal. So rational numbers can turn out to be integers. All right, you can see that this box is inside the rational numbers, whole numbers, or natural numbers, or they might not be integers, whole numbers, or natural numbers, and instead they're fractions or decimals. And the fractions, when you turn them into decimals, are always either terminating or repeating. Okay? So this pretty much covers the numbers that we use, but there is another operation that we can do that has to create one more set of numbers. All right, so that last set of numbers are called the irrational numbers. And the operation that gives us irrational numbers is the square root. If we take the square root of something that's not a perfect square, say the square root of 2, we get something like 1.414, and it keeps going over and over and over again. And that's not a rational